Hello, we are discussing about fourth lecture in the series of pulse and digital circuits course. In the last lecture, we discussed about the importance of capacitance, that is, the operation of capacitor, how it charges and how it discharges, how much amount of time does it take to reach a particular value of voltage. Okay. Otherwise, within given time, how much voltage can be attained by the capacitor. Overall, we have seen how to calculate voltage across capacitor at any instant of time. That's what we observed in the last class. And we also observed one more important point. For a capacitor, if you apply a constant voltage, then the voltage across capacitor rises exponentially towards that voltage with respect to constant of the circuit, with respect to circuit constant. It doesn't depend on the final value, that is what constant voltage you are applying. It only depends on the circuit time constant. To reach the final value, that is to reach the applied constant voltage, capacitor requires minimum 5 time constants of time. That's what we observed. So with the help of that knowledge, now we are going to discuss about response of LP-RC circuit, low pass RC circuit for a step input. If a step input is applied, how the output voltage of LP-RC circuit, which is nothing but capacitor voltage, okay, that we are going to draw. From that one we are going to define an important parameter as rise time. Then we are going to discuss about relation between rise time and bandwidth, okay, and afterwards we will see how to solve a simple problem. So this is today's lecture. Let us start with response of low pass RC circuit for a step input. We know that one step input is going to be looks like its sudden change at one instant of time. Sudden change at one instant of time. So generally we will take it as t is equal to 0. At t is equal to 0, we are going to apply a sudden change in the voltage. This is what we can call it as step. So you are stepping up from this point to this point. Looks like step, sudden change. Okay. And arbitrarily I am assuming it as this is V volts. It can be 1 volt or 0.5 volts or any voltage greater than 1 or less than 1. Simply I am going with arbitrary voltage as V. V constant voltage is applied for the low pass RC circuit. And since it is constant, so constant voltage is applied across capacitor. The capacitor voltage rises exponentially towards that value. It requires minimum 5 time constants of time to reach that value. So before applying this voltage, circuit is initialized with 0, so capacitor voltage is also 0. At t is equal to 0, a step of V volts is applied. So to reach step of V volts, capacitor takes some amount of time, that is referred as 5 time constants to reach the final value, and afterwards it will be constant. So this point we can say it as 5 tau. Okay. So this is based on time constant. Time constant is nothing but tau. Time constant of the circuit is product of R and C. Okay. So now if somehow if you are changing either C value or R value, you don't get the same waveform. You may get either faster rising waveform or slower rising waveform depending on the time constant. So I assume that one more case, tau is equal to R2 into C. Somehow resistance is changed, so the time constant is changed. So with respect to the time constant, you may get a faster response. If tau 2 is smaller than tau, so smaller time constant means capacitor rapidly charges. Okay, so we can draw like this. Okay. Whereas to reach the final value it requires 5 time constants, that is 5 into tau, but tau is very small, so 5 into tau is very small compared to this 5 tau. So this is 5 tau 2. And if you are changing either C value instead of changing R, okay, so by that time you may get tau 3. Tau 3 is nothing but R into C2 for example. Okay, that's some C value. So this tau 3 for example, if it is greater than tau, that is the first case, white color case is tau. So for this tau 3, if it is greater than tau, it takes even longer time. it takes even longer time. So by the time the output response is going to be taken longer time to reach the final value. So this will become 5 tau 3. So based on the time constant, the output waveform is going to be output waveform is exponential only, but how much time it is taking, that will change. If the time constant is smaller, it takes small amount to reach the final value. If the time constant is large, it takes longer time to reach the final value. Okay. This is the response of low pass RC circuit for a step input. This is all depends on only one important point, that is when a constant voltage or a step signal is applied to a RC circuit, the voltage across capacitor starts charging exponentially and it reaches the final value minimum of 5 time constants of time. Based on this one, we can draw the output waveform for the given time constants. And we can also calculate voltage across at any point. If you want to calculate the voltage at this point, or at any point, if you want to calculate, okay, we are going for the general equation. General equation is this one. Voltage across capacitor at any instant of time can be calculated using Vc of t is equal to Vf minus Vi into e power minus t by ti, t minus ti by Rc. This, by using this equation, you can calculate voltage at any instant of time. Otherwise, at any instant of time, how much time it requires to reach a particular voltage. Okay. Now we are going to define rise time and we will derive the expression for the rise time. So calculation of rise time is our next point. This blue color line is the output response of low pass RC circuit whenever step input of V volts is applied. We know the definition of rise time. Rise time is defined as time required for the output to reach from 10% to 90% of its maximum value. Rise time is defined as the time required for the output to reach from 10% to 90% of its maximum value. Maximum value is nothing but V volts. Since you are applying V volt step, capacitor can take V volts. So 10% of V is 0.1 volts. 90% of V is minus 0.9 V. So draw horizontal lines at 0.1 V and 0.9 V where it is touching. Those are the two times. 0.1 V is touching at this point. Okay, so make it as this is the point T1 and 0.9 is touching the output waveform at this point, which is T2. So rise time can be defined as TR is the difference between these two times. Time required for the output waveform to reach from 10% to 90%. So TR can be defined as T2 minus T1. T2 minus T1, where T1 means T1 is a time required to reach 10% of its maximum value from initial value. From initial value means 0. Okay, so T1 is the time required for the output to reach 10% of its maximum value, that means 0.1 volts from initial value. Next, T2 is the time required to reach 90% of its maximum value, that is final value from initial value. So to reach 0.9 volts, how much time it is taking, that is T2. To reach 0.1 V, how much time it is taking, that is T1. From initial value means from 0 onwards. TR is equal to T2 minus T1. Now the difference between these two times is nothing but rise time according to the definition. We will see how to calculate T1 and T2. Next, TR. So calculation of T1 can be done if you know the equation. Voltage across capacitor at any instant of time can be calculated by using this relation. Already we discussed so many times. So in this one, what we require is what is Vf, what is Vi, what is Ti. Rc is nothing but circuit time constant. For the given R and C values, you can calculate Rc. So final value, Vf means final value, that is voltage across capacitor at t is equal to infinity. So if you apply the input voltage for infinite amount of time, how much voltage can be stored by the capacitor? Definitely it will be that voltage. So since you are applying V volts, Vf is equal to V. And next, initial value at starting. Okay, what is the voltage across capacitor? This is 0. Voltage across capacitor is 0. Vi is equal to 0. So next, Ti. Ti is the starting time at which input voltage is applied. Input voltage is applied at t is equal to 0. So Ti will become 0. And we are going to calculate T1. We know the voltage across capacitor at t is equal to T1, that is 0.1 V. So that's what I have written. At t is equal to T1, voltage across capacitor is 0.1 V. So 10% of final voltage is reached by the capacitor at the time of T1. Since V is the final voltage, 10% of it is 0.1 V. From general equation of Vc of t, from this equation, okay, substitute Vc of t. So small t should be replaced with T1 now. So Vc of T1, that means 0.1 V is equal to V final is V minus V initial is 0 e power small t should be replaced with, okay, T1. Ti is equal to 0. So T1 minus 0 is T1. Directly I have written it as T1. Okay, T1 divided by RC. So V get cancels if you take V common from this expression. Later, after simplification, e power minus T1 by RC is equal to 0.9, and take natural logarithm on both sides. So e and natural logarithm get cancels. Minus T1 by RC is equal to natural logarithm of 0.9. So T1 will be equal to 0.1 RC. So this is we can find. Next, after calculating T1, we can calculate T2. In the same way, T2 is the time required for the capacitor to reach 90% of its final value. So 90% of its final value means 0.9 V. V is the final voltage. Okay, and for this one also it is starting from initial. Starting from initial is nothing but again it is 0 volts. Final value is V. Initial voltage is 0. That is, initial voltage means voltage across capacitor at the time of input application. That is 0. Ti is the initial time, that is starting time at which input is applied, that is also 0. And we know at t is equal to T2, voltage across capacitor reaches 90%, that means 0.9 V. Substitute all these values in the general expression of Vc of t. So now small t should be replaced with T2 because we are interested in T2. Vc of T2, that means 0.9 V. Vf V, again Vf is V. V initial 0 e power small t should be replaced with T2 and Ti is 0. T2 minus 0 is T2. So minus T2 by RC. So take V common from this expression. If you take V get cancels. So e power minus T2 by RC will be equal to 0.1. Take natural logarithm on both sides. E will get cancels. So from that one you can calculate T2. T2 is 2.3 RC. Since you know T1 and T2, you can calculate the rise time. Rise time is the difference between T2 and T1. So 2.3 RC minus 0.1 RC. It will be equal to 2.2 RC. This is the expression for rise time. TR is equal to 2.2 RC. Okay. So rise time of the output waveform is totally depending on time constant of the circuit. Okay, it doesn't depend on the applied input voltage. Again, rise time of the output waveform is totally depending on time constant of the circuit. It doesn't depend on the applied voltage. Remember that point. Next, we'll go for the relation between rise time and bandwidth. We have already calculated bandwidth of low pass RC circuit. Okay, bandwidth of low pass RC circuit we calculated from the frequency response. Okay, when a sinusoidal input is applied. So this is what frequency response of LPRC circuit. LPRC circuit act as low pass filter which passes all low frequencies up to a cutoff frequency. That cutoff frequency is called as upper cutoff frequency FH. Okay. So this is FH. This is the frequency response curve for the low pass RC circuit or low pass filter. And from the general definition of bandwidth, is the range of frequencies over which the gain is greater than or equal to 70.7% of its maximum value. So if you assume gain is equal to 1, maximum gain is 1, then 70.7% of its value is 0.707. First put a dot on magnitude, that is y-axis, at 0.707. Draw a horizontal line where it is touching the frequency response. That point will become fH. And this is the lowest frequency it is allowing, and it is the highest frequency it is allowing. So from this one, bandwidth of this circuit is highest minus lowest frequency, fH minus 0. fH minus 0 means fH. Bandwidth of low pass RC circuit is fH. Already we defined this one, where fH is upper cutoff frequency, that is circuit dependent. That means the circuit elements it depends on. fH is equal to 1 by 2 pi RC. Okay, that means bandwidth. So this is equation 1. Already we calculated rise time. Rise time is also depending on RC, and bandwidth is also depending on RC. So write RC in terms of bandwidth. So from this expression, we can write RC is equal to 1 by 2 pi into bandwidth. Substitute this second equation in first one. So TR is equal to 2.2 into 1 by 2 pi bandwidth. 2.2 divided by 2 pi, okay, equal to 0.35 divided by bandwidth. So bandwidth is nothing but upper cutoff frequency for low pass RC circuit. So bandwidth is now replacing with fH. TR is equal to 0.35 by bandwidth you can write, or 0.35 by fH also you can write. Okay. Otherwise, multiplication of TR and bandwidth is equal to 0.35, or TR into fH is also equal to 0.35. Okay. So from this one, rise time is inversely proportional to upper cutoff frequency. Rise time of RC circuit is inversely proportional to upper cutoff frequency of it. Generally we know that one, time and frequency are inversely proportional. The same thing here also. Rise time is inversely proportional to upper cutoff frequency. This is relation between rise time and bandwidth. Okay, now we will go for an example for the response of LPRC circuit when a step input is applied. Look at this one. There is a RC circuit given whose R value is 50 kilo ohms and capacitance value is 500 picofarads. A 10 volt step which is starting at t is equal to 0. A 10 volt step starting at t is equal to 0 is applied as input for this LPRC circuit. First we are going to calculate rise time. Next, time required for the output to reach 63.2% of its final value, and voltage across capacitor at t is equal to 100 microseconds. Next, time response to reach 7.8 volts by the output waveform. Output waveform is nothing but simply voltage across capacitor only. Next, time required to reach 4.8 volts by the voltage drop across resistor. So how much time does it take to reach voltage drop across resistor is equal to 4.8 volts? That we are going to calculate. These are the 5 things. Okay. And we know that one, for a capacitor, when a step input is applied, that is when a constant input is applied, then capacitor charges towards that value exponentially with circuit time constant. So this is the output waveform. The green color says output waveform, and this is input signal. 10 volts step is applying and capacitor is charging towards 10 volts exponentially. We know that one, rise time is a difference between rise time is the amount of time required to reach the output waveform from 10% to 90% of its final value. Already we calculated that one as TR is the rise time, which is 2.2 times of RC. So this is 2.2 into R means 50 kilo ohms and 500 picofarads. So this will be 2.2 into, and it is 25 microseconds. So totally it will be equal to 55 microseconds. Rise time is equal to 55 microseconds. Okay, that is first answer. Second one, the time required to reach 63.2% of its final value. We no need to calculate anything for this one, because with respect to the definition of time constant, tau, time constant for a RC circuit is R into C. That means R is 50K and C is 500 picofarads. 500 picofarads. 500 picofarads. So it will be 25 microseconds. So 50K into 500 is equal to 25 microseconds. 25 microseconds is the time constant. By definition of time constant is the amount of time required to reach the output waveform to reach 63% of its final value. Is the amount of time required for the output waveform to reach 63.2% of its final value. So the time required is 25 microseconds. If the output to allow for 25 microseconds, it will reach 63.2% of its final value. Third one. Voltage across capacitor at T is equal to 100 microseconds. Voltage of capacitor at 100 microseconds. So that means at T is equal to 100 microseconds, what is the voltage across capacitor? To calculate this one, we should know the general equation of capacitor voltage at any instant of time. Okay, that is this one. Voltage across capacitor at any instant of time is given as Vc of t is equal to Vf minus Vi into e power minus of t minus Ti by Rc. Where for this one we will see Vf means final voltage of capacitor. That means capacitor voltage at t is equal to infinity. If the input voltage is applied for infinite amount of time, how much voltage can be charged by the capacitor? That is stated as Vf. Capacitor voltage at t is equal to infinity. So always it will be equal to the input voltage applied. So 10 volts. Next, Ti. Initial time. The time at which 10 volts is applied. Initial time, the 10 volt, that is starting time at which this 10 volts is applied. 10 volts is applied from the waveform. It is at t is equal to 0. So Ti will become 0. Next, Vi. Vi is the initial time or starting initial voltage. Vi is the initial voltage, that is starting voltage of capacitor when 10 volts is applied. At the time of 10 volts is applied, that is at t is equal to Ti, what is the voltage across capacitor? Voltage across capacitor shows this green. So before that one we have not applied any voltage, that is 0 volts is applied, so capacitor is uncharged. It has not charged any voltage as you are not applying any voltage before t is equal to 0. So initial voltage is 0 and Rc value is 25 microseconds. Okay. So Vc of t will become Vc of t at 100 microseconds. In this equation substitute all these values with t as small t is equal to 100 microseconds. So this will become 10 minus of 10 minus 0 into e power minus of t minus, that is 100 divided by 25. So it will be 10 into 1 minus e power minus 4. So it is around 98%, that means 9.8 volts. Okay. So if you assume this is 100 microseconds, then the charge stored by this one is at 9.8, the voltage charged by the capacitor is 9.8 volts. Okay, at t is equal to 100 microseconds, this is voltage across capacitor, 9.8 volts. Next, find the time required to reach 7.8 volts by the capacitor. Find the time required to reach 7.8 volts by the capacitor. So at what time voltage across capacitor is equal to 7.8 volts, that we are going to calculate. So say this is the point which is 7.8 volts. Draw a horizontal line and it is intersecting the output waveform at this one. Project this one onto x-axis. So this is the time required. How much is the time? Okay, where the capacitor voltage is equal to 7.8 volts. Again we are going for this one. This is an important equation, voltage across capacitor at any instant of time. From this one you can calculate two things. If you know voltage across capacitor, you can calculate how much time it takes to reach that value. And if you know how much time you are giving as input, you can calculate how much voltage a capacitor can charge. These are the two things you can calculate from this equation. So again you are going to use this equation, okay, to calculate the time. So for this one, V final is 10 volts, already we discussed it. V initial is 0 volts, T initial is 0 volts, and time t we are going to calculate. Okay, Vc of t is 7.8. Substitute all these values. 7.8 is equal to 10 minus of 10 minus 0 into e power minus t by 25. So from this one, 7.8 is equal to 10 into 1 minus e power minus t by 25. Okay, 0.78 is equal to 1 minus e power minus t by 25. So if you take e power t by 25, this term, if it is coming this side, positive it will become, and 0.78 if it comes over this side, it will become 0.22. So from this one, t is equal to, it will be around 37.2 microseconds. The value is not exact, it is approximate. And you can confirm that one, this time has to be less compared to previous 100 microseconds. By the time of 100 microseconds, the capacitor is reaching 9.8. Okay, now it has to reach 7.8. That means it has to be less only. Okay. And next case, the last one. Okay, how much time it takes to reach the voltage drop across resistor to reach 4.8 volts. So we are going to calculate at what time voltage across resistor will be equal to 4.8 volts. So if you observe the RC circuit, okay, and this is input signal Vs and it is VR, this is voltage across capacitor. From KVL, can I say that one Vs is equal to VR plus Vc, because voltage current is flowing in this direction, so this will become plus minus, this will become plus minus. So if you apply KVL, Vs is equal to VR plus Vc, otherwise VR is equal to Vs plus Vc, else Vc is equal to Vs minus VR. This is Vc minus VR. This is Vc, Vs minus Vc. So resistance voltage drop across resistance is equal to subtraction of capacitor voltage from source voltage. Otherwise, if you know voltage drop across resistor, you can calculate voltage across capacitor. Since you know the input voltage, if you know voltage drop across resistor, the remaining voltage should be across capacitor. If you know the voltage across capacitor, the remaining voltage should drop across resistor. So these two are the important equations which are from simple KVL formula. And we know only one equation. We can calculate voltage across capacitor at any instant of time. Okay, so that can be calculated using this general equation. So we are going to find at that time how much is going to be capacitor voltage. From that one we are going to calculate time. So at what time VR reaches 4.8 volts, okay, by the same time voltage across capacitor will be equal to 5.2 volts, so that the sum of these two will be equal to 10 volts. So when resistor voltage drop is equal to 4.8, by the time capacitor voltage reaches 5.2, we will use this equation to calculate T. So that is the time at which voltage drop across resistor is 4.8. Substitute 5.2 is equal to Vf. Vf value is 10, Vi value is 0, Ti value is 0. Okay, RC is 25 microseconds. 5.2 is equal to 10 minus 0 into e power minus t by 25. So this will be 5.2 is equal to 10 into 1 minus e power minus t by 25. Next it will be 0.52 is equal to 1 minus e power minus t by 25. E power t by 25 is equal to 0.48. 1 minus 0.52 will become 0.48, and you can calculate t taking natural logarithm. If you take natural logarithm, okay, at that time it will become t by 25 is equal to natural logarithm of 0.48. Next, t is equal to 25 into natural logarithm of 0.48. So this you are going to calculate, and the value of this one, if you observe, wait a minute, into 25. So you can calculate this one. Okay, calculate this one. So from this diagram you can write, at this point capacitor voltage is 5.2 volts. Okay, thank you.